All right. Welcome to Intro to Data Science, Linear Regressions, a much sought after workshop. So excited to get this going. My name is Jelani Thomas. I am the marketing program manager. Sorry, product marketing manager. That was my old title. Product marketing manager for data science. And I'll be here to sort of field all the questions in the chat and or the Q&A, but please direct most of your questions to the Q&A just so we have a place to sort of organize it. And with that being said, I will pass it over to Abanit. If you have any questions about like the Flatiron School experience and stuff like that, we won't get to that in the workshop itself, but we'll leave time after the workshop to kind of get to some of those, maybe like a few experience type of questions. So cool. With that being said, let's just jump right in. Abanit, I'll hand you the floor and I'll be monitoring the chat.
Awesome. Thanks a lot. I'm going to go ahead and share my screen here. Can everyone see the screen?
A lot of yeses, a lot of yeses.
Okay, awesome. All right. And if I hit the present button, does that still work for everyone? Okay, yep. Awesome. All right, so today, as the title of the event suggested, we're going to be talking about linear regression. It's extremely, it's one of the simplest algorithms in machine learning. It's one of the first things that you will learn if you try to go and learn machine learning. Essentially, the goal here is we have something called the statistical learning theory. It's essentially a theory that's based on the idea of using data and statistics together to provide a framework for building a machine learning algorithm. The idea is to construct a statistical model that can draw certain conclusions from the available data, and then use this model that we just built to make predictions about what the future holds for us. So before we get too much in depth with that, just a few quick things. There are different types of data variables. Remember that when we talk about programming, a variable is essentially anything that can hold information. There is something called a dependent variable, so data that can be controlled directly. You have other names for this like outcome variables, target variables, response variables. Common examples include, someone's monthly income, could be the price of a home, could be the temperature of a controlled environment, something like that. We also have independent variables, so data that cannot be controlled directly. Other names are, input variables, explanatory variables, features, predictor variables, something like that. Common examples include age, day of the week, essentially time-related things that are pretty much out of our control. So with that being said, let's talk about how to establish relationships between variables and how to kind of like look at these things. So dependent variable depends on the independent variable. As we just mentioned, the dependent variable is one that can be controlled. Independent variable is one that cannot be controlled directly. So in here, what we are doing is we're plotting age versus the monthly income. The monthly income is in thousands USD. So you can clearly see that as the person's age increases, their monthly income does tend to increase quite a bit. And that is exactly what we're kind of like showing here. Again, a great way to figure out the relationship between different variables is to try to use a plotting technique. Generally speaking, this type of a plot is called a scatter plot, where you essentially have pairs of observations. So you have an age and you have a value for the monthly income. So all that we did was we plotted all of such data available to us, and we tried to draw a line through it. We'll talk about how to draw that line. But essentially, all we are doing here is we are trying to plot the independent variable versus the dependent variable. Okay, so now that brings us to the next part, which is statistical modeling. A statistical model can be thought of as some kind of a thing to do with the data that allows me to express my dependent variable as a function of one or more independent variables. Again, remember that the dependent variable was the one that I can control, and the independent variable was something that I cannot control directly. So I'm trying to express something that I can control in terms of things that I can't control. So the idea is that there are things like, the independent variables essentially. So imagine something like age. If I know the age, can I guess the person's monthly income? And why would I want to do that? Well, there can be multiple things, just in a company, they might want to like some sort of create some sort of a model around how a person's monthly income, how an employee's monthly income increases with their age. They might want to, like, even just like government entities in general could want to see how their population's income increases or something like that. Again, if we consider like house prices in an area, we want to know what the house price might be 6 months from now. Again, plenty of such applications for trying to determine what exactly might be the result at some point down the road. And a statistical model defines this relationship between the dependent and an independent variable. So essentially just trying to find out a relationship that will allow me to make a future prediction on the dependent variable based on the independent variable. Okay, and that brings us to linear regression. Now, regression in general is a subset of problems where we want to determine what the future value of a dependent variable might be, given that we know the values of one or more independent variables. So again, regression is a subset of problems where we want to determine the future value of a dependent variable, given that we know the future values of one or more independent variables. So as I mentioned, trying to predict the income if we know someone's age. And the most common form of regression analysis is linear regression. And the main constraint, or the main reason why it's called linear regression, is that we only explore linear relationships. Linear relationships are of the form y, which is like the variable that we want to determine, is equal to mx plus something. So in a linear relationship, we are only exploring the first power of the relationships.
Abhinav, real quick.
Yeah.
Just a question. Is the line that was plotted considered a line of best fit for the data? It was asked because it's used heavily in this person's engineering course, and they wanted to know if it was the same concept.
Exactly. We'll get to the best fit in just a little bit, but essentially what the best fit actually means is that if I go back to that slide, if I go back here, I can draw a whole set of lines. So why not this line? Why not that line? Why only that line? That's because that line will actually help me model the data the most in the most accurate manner, and that's why we call it the best fit line. And again, we'll talk about that in detail in just a little bit. Okay, so that brings us to simple linear regression. Now, a simple linear regression model would essentially fit a line to the data points as shown in the previous slide. This line can then be used to kind of like describe, what the behavior would look like. Again, another great use of this line is I can extend this line in the future and try to predict what the income would be for certain other ages as well. And again, I can extend this line on the left side as well to try and predict what the income would be for certain other situations. So yeah, that's the main thing. Also, another use of that line is I can try to predict values for which I don't have any information of monthly income. But let's say, I want to predict the income at age 55. I know for 50, it's somewhere around here. For 60, it's somewhere around here. So for 55, I could potentially try to figure out a line that kind of like goes somewhere like this and use that line as kind of like a guiding line or a guide to kind of like figure out and conclude that this right here is going to be the income for each. That probably looks like 54 maybe. So yeah, so that is simple linear regression in just a little bit. So essentially what we try to do is we try to model a linear relationship with the target, the dependent variable, by fitting the best straight line to describe this relationship. Remember that the line will always be a straight line. You can't have like a weird curve in it, because a curve will not be a linear relationship. So linearity is the most important part here. Okay, so let's go to the next slide. Okay, so
question before we move on. Does the fit line take into account the uncertainties on the data points?
It does to a certain extent. Obviously, if we try to take into account every single uncertainty, we probably won't be able to come up with a line that fits the data entirely, but we try to accommodate as much as possible. Yeah. So the equation of that line can be written out by this small thing: y is equal to mx plus c. That is the equation of a straight line. Four main components to that: y, that is the dependent variable that needs to be estimated and predicted. Then you have m, the slope of the line, essentially how tilt, what is the tilt to that line. You have x, which is the independent variable, and you have c, which is the point at which the line intersects the x-axis. So if I go back one slide, right here, the tilt, the right that you see right here, this sort of a tilt, that's the c. Your y is right here, your x is here, and c would be the point at which, if you kind of like extend this line, what point does it hit that x-axis, or this particular point right here. So what point do the two lines intersect, essentially, like the y-axis and the x-axis? What would be the in this case, it would be what is the income of a person at age 0, essentially. Now that might not sound correct, but the data we have leads us to that sort of a conclusion. Okay, I see there is one question here. The line describes the behavior of the data in a way, yes, but remember that the rate of change will stay constant. So when we talk about derivatives, we are talking about the rate of change, and the rate of change, because we are only exploring linear relationships, will stay constant. Okay. All right, so continuing, that's simple linear regression. Notice that we are only considering one independent variable in here. So we are only considering one value of x so far. And that is the biggest limitation of simple linear regression, in that it only allows us to model the relationship between an independent variable and a dependent variable. But in many instances, we know that there is more than one independent variable that will influence the dependent variable. So the monthly income of a person is not only dependent on age, but it's also dependent upon their education level, their seniority in a company, the years of experience that they have in a certain industry as well, for which the simple linear regression will not be able to account for all of these different things. And that is where we go to multiple linear regression. Now, multiple, as the name itself suggests, tries to predict the dependent variable by looking at more than one independent variable. So because we noticed that there are more than one independent variables that could influence our dependent variable, we now need to complicate our the equation that we had originally a little bit more. And that's just because we want to consider the impact these other things will have as well. Okay, so here is what our previous model would look like if we added in years of education, for example. So the estimated monthly income would be equal to the slope of seniority or the slope of age plus the slope of years of education as well, plus the intercept. Now, the general form of such a model, when we extend it out, becomes takes this sort of a format, the formula that you see right here, which is y hat, which is nothing but the predicted value, is equal to b0 or beta 0. Beta 0 is the intercept right here. Plus, you will see that there are a bunch of x's and there are a bunch of corresponding beta values as well. The beta values in here are nothing but the coefficients associated or the slopes associated with those x independent variables. So x1 to xn are all of the independent variables that we want to consider, and beta 1 to beta n are the slopes associated with those variables. And then beta 0 was the intercept, the value, and everything else is 0. And then y hat is our predicted value of the dependent variable. So that's a little bit about what exactly multiple regression is all about. And again, multiple regression tries to solve the main problem of simple regression, which is that it only takes into account one thing, whereas in many instances we know that there are multiple different things that tend to influence the price of a home or something like the income of a person. So now we'll kind of like look at how to build linear models and just talk a little bit more about simple regression, multiple regression, and interpreting those models. But we will switch to a Jupyter notebook, which is going to be the software that we use here. So any questions until this point?
We got one here. How do we know if a linear fit model best describes our data and not some spline or cubic or exponential fit?
That is a great question. That is a great question. We will talk about a metric called the R squared value, which is essentially going to help us determine how much variation in our dependent variable is explained by our current linear model. If that R squared value comes out to be extremely low, that's going to be on a scale of 0 to 1. If that comes out to be extremely low, then we conclude that this model that I have is not great at describing the dependent variable or the variation in that dependent variable. And if that value comes out to be extremely high, then we can conclude that this model is fairly good at describing the variation, and we can use that model. But if that not exactly the correlation coefficient, no, this is called the coefficient of determination, but we will talk about that in just a little bit. So okay, all right, coming.
So question, one more question before we head on. So we need to plot our data set before we decide to proceed in a prediction using linear regression, right?
Ideally, the plotting of the data is done to determine that there is a linear relationship or not. It's just kind of like a visual way to confirm whether we even have a linear relationship and can we use linear regression here. But you don't need to plot the data now. And when you have multiple such features, plotting actually becomes really hard in multiple regression, because remember that when we have more features, that means there are more point or more things that we can potentially fit on, then we can potentially perceive using the 3 dimensions. So it gets a little difficult. Once we get to an example of multiple regression, I think that will make a lot more sense. Can that beta on the alternative model be treated as a constant? Do you mean this beta 0 right here? If so, then yes, that is the intercept. It will be constant, yes.
Yeah, just
but
so
the
everyone
beta
knows.
1 to beta
I was just
A,
going to read the
beta n
question.
are, sorry, yeah.
Sorry, I was just going to read the question. The question was, can the beta on the alternative model be treated as a constant?
Yeah. So for that, if you're talking about this beta 0, then yes, that's correct. If you're talking about beta 1 to beta n, those are going to be the slopes and they will vary for each feature. Okay, so continuing with simple regression, as someone just mentioned, the correlation coefficient. The correlation coefficient essentially is a way for us to check how do the variables vary together. And we can actually do that by plotting as well. Like the correlation coefficient is just one way for us to describe that. But let's take a look into what exactly helps us determine and build this simple linear regression model. So remember that the equation of a line was y is equal to mx plus c, where y was our dependent variable, x was the independent variable, m was the slope of the line, and c was the intercept. So expanding on that, the best fit line slope, as I mentioned, we can draw multiple lines. We need to figure out which is the best one. And that can be done by actually using this particular formula. I'm not going to go into the detail of that formula just because it will take too much time. I have the Wikipedia page linked right here to look into the derivation of the formula. It might not make a lot of sense right now, but take a look at the second formula. That should make a lot more sense, hopefully, which is essentially the mean of the independent variable, x bar, mean of the dependent variable, y bar, x bar times y bar minus xy bar, which is essentially their multiplication, divided by the square of the mean minus the mean, the mean squared, essentially. So again, this formula might make a little more sense. Don't need to go into the derivation of that. There is a very strong mathematical proof behind this, but we don't need to go into that just because of the time. Okay, so in here, I'm just importing a few libraries to get my data set up. And I'm just using some random data because that is more comfortable to use here. So just plotting that data, you can see that there is a linear relationship and that I could potentially draw a line that looks something like this, maybe, to kind of like get the best possible fit. Now, obviously, I could draw lines that go like this as well, that go like this as well, but those lines are not going to be ideal fit, because if I wanted to calculate the dependent variable's value for an independent variable whose value is probably like, let's say 7, I know that it's going to lie between that 6 to 8. So I can draw this line right here, and I can draw that line right there to kind of like predict the value of where the independent variable was 7, and kind of like get that answer. So again, we'll go into how we calculate the best line in just a little bit, but yeah. Okay, so for calculating the slope of the line, we're just going to use this formula directly. Just going to put in all of my values in here, and if I just like use the formula correctly, this is the returned answer that I get, which is 0.539. So essentially, what this is telling me is that, again, formula has a solid mathematical derivation, but if I just plug in the values, what it tells me is that the slope of my line is 0.53. So does the multiple regression translate to multiple independent variables? Yes. As I just mentioned, in simple regression, you only take into account one independent variable. And oftentimes you will notice that whatever the dependent variable you're trying to investigate is dependent on a lot more things and not just one particular thing. So that's why we need multiple regression. Okay, so now that we have that m bar, or we have that m, we know what the x bar is, we know what y bar is. we can easily calculate the intercept, which is just going to be a straightforward subtraction. I calculated that, and that comes out to be 6.37. Again, simple mathematics here, calculating X bar, calculating Y bar. We already found out that the slope is 0.539. So we can easily go ahead and calculate the intercept. Once we have both of those, we can actually go ahead and calculate that regression line fairly easily. And we can actually write the equation of the line as y is equal to 6.37. 6.37 was our intercept, plus 0.53x. So once we have that equation, we can actually plot that line. And now what I can do is I can use this line to predict future results. So imagine that the value of the independent variable is 7, and I want to predict the value of my dependent variable, which I can just plug 7 into this equation right here and easily find out that answer, and that comes out to be 10.155. And I can plot that on that line, and you can clearly see that that is lying right on the line, which is expected, and that my line is essentially giving me exactly what it's supposed to. So that's how we would use simple linear regression. Again, this is just a quick example. We are not talking about whether this line is the best line yet or how to identify that. We will talk about that in just a little bit.
Question for you. Does the multiple regression translate to multiple independent variables?
Yes, it does. That's where these x1 to xn come from. They are all different independent variables. Any questions about simple linear regression?
Can you use this model to predict a value of y for a value of x that is outside the data set? In this case, 14 or 16.
You can, but the accuracy of the value might be a little lower, just because the statistical model is only as good as the relationships that it has seen. If it just hasn't seen a value of 14 or 16 before, it can't do a good job of predicting the dependent variable's value for that particular number. But it will give you some sort of a prediction. It might not be accurate, but it will be better than what you have right now, which is nothing. Okay, so I think we can proceed to multiple regression. Okay, we have a few more questions. What are the normal limitations of this model despite data that don't behave in a line? Okay, so simple linear regression definitely does have a lot of linear regression in general does have a lot of limitations. It is one of the simplest models that we have access to. So it is definitely going to be, not the most ideal model for a lot of different types of data, but we do try to use this just because it's so easy to build and it's so easy to interpret. And we'll talk about what I mean by that in just a little bit. How would you filter out outliers? Okay, that's a great question. Generally, by looking at the frequency of the data, if you have 100 data points, you will see that they tend to follow a distribution that at least looks somewhat like this, where a huge amount of values are repeated fairly frequently, and a lot of values are not repeated frequently. So any values that kind of like fall in here and fall in here would essentially be treated as outliers. These are like, here is frequency of the values occurring, and here are the values itself.
What are the normal limitations of this model despite data that doesn't behave as a line?
So when data doesn't behave as a line, we do have other models that will be much better suited. But other limitations do include certain problems where our independent variable is not actually behaving as an independent variable. And we will talk about that in multiple regression in just a moment. Linear regression is used frequently in the industry, especially for predicting like sales, for example. Like in the retail industry, if you want to predict sales, if you want to predict how much inventory to keep on hand for a certain item, these models are used fairly significantly because you can interpret these and customize these models very easily. Also, it's very easy to get a lot of data and perform this sort of a model fairly quickly. So you can iterate very fast and you can design different prototypes really quickly and just go from there. How the uncertainties on the data were accounted for, you're correct. With this model, we don't really account for a lot of uncertainties on the data. But again, the main reason for that is that this is the simplest model that we have access to. Oftentimes, you will end up using a lot more complex models, which do have a lot more robustness and which can account for a lot of different inconsistencies in the data itself. So, okay, let's move on to multiple regression at this point. Okay, so as I mentioned, simple linear regression, you only have one dependent variable and one independent variable. When you go to a multiple regression model, you have multiple independent variables that are having an impact on the dependent variable. So an example would be the price of a home, maybe depends on the number of bedrooms in the home, the area that the home is located in, probably the season in which the house is being sold, proximity to public transportation, maybe, and like a lot of other things as well. So to account for all of that, we do need a little more of a complex model, which is what multiple regression is. Now, before we actually jump into building models, we need to talk about two very common things that we do encounter when using when we're building these sorts of models. One is the whenever we have categorical variables. So categorical variables, as you might have guessed, are not numerical features, but rather these are categories. Each category can mean something different. So imagine going back to the income example, you have a variable for let's say education level, right? You have maybe bachelor's, master's, and PhD, right? So now if I put bachelor's as 1, if I put let's say master's as 2 and PhD as 3, in my data it shows up as 1, 2, 3, but it doesn't actually mean 1, 2, 3. 1 means bachelor's, 2 means master's, and 3 means PhD. So I need to be able to account for these different categories when I am building my models. So let's quickly look at this. The data set that I'm using here is called the Auto MPG data set. It's a fairly famous data set. If you just Google Auto MPG data set, you'll find plenty of analysis being done with this data set. Now, in this data set, I do have a bunch of different columns. In here, the dependent variable is miles per gallon. And I have a lot of these different technical specifications of the car, including the model year, the origin of the car, the name of the car, which are all kind of like being used to help me determine the miles per gallon. So there are some manufacturers of cars who are famous for making very efficient cars, very fuel efficient cars, whereas there are certain other manufacturers who prefer to make luxurious cars, which are not that fuel efficient as well. Now, we have this variable in here called origin. Now, the origin variable actually is just telling us which continent was the car manufactured on. So we have one, there are only 3 values in here. And if you look at this, you'll see that the minimum is 1, the 75% is 2, and then the maximum is 3. And then we also print that out, and it is exactly 3 different types of values. Now, these 3 different types of values just mean the continent in which they were manufactured, probably. One probably would mean something like Asia, two might mean Europe, and 3 might mean North America. So, but the way these are entered into my data set makes them look like they're integer values, but they are not numerical features. They are categorical features. So variables like these cannot be used directly in regression models. And we do need to take special care before we can use these variables directly in our models. And the best way to identify these variables is by trying to plot them against the dependent variable. So remember that my dependent variable in this data set was miles per gallon. If I plot something like acceleration, this is what the plot looks like. And I can easily imagine drawing a line through that plot, right? So if I just try to draw a line, it could be something like this. So there is a pretty clear linear relationship between acceleration and miles per gallon. But if I try to draw a similar line for cylinders, for example, I really can't draw. I could potentially draw a line like that looks like this. Not a very good line. Similar thing for origin. Again, I could draw this, but half the data pretty much lies beyond that line already. So this is like a good indication of if you only have values that take on anything from a certain range. So like 3, 4, 5, 6, 7, 8, something like that. That's an indication that you are dealing with a categorical variable. And in cases like these, what you want to do is you want to create dummy variables. Essentially, what that means is you create a separate column for each of the category, and your final data might look something like this, where we started with this, but we created a new column for every cylinder that we had. We created a new column for every year that we had, and we also did that for origins as well. So we are creating a new column for each and every category that we encountered in our data. You can just Google this. I'm sure there are tons of articles out there that will help you understand these techniques a little better. In the interest of time, we won't be diving deep into this. Okay, now another problem that we need to consider before building a multiple regression model is, now because we have these different variables, these different number of independent variables, it is highly possible that each one of those independent variables interact with each other. Ideally, an independent variable is supposed to like only interact, or a change in that independent variable is supposed to only impact the dependent variable. But oftentimes, because these independent variables are not exactly independent, but rather they are all closely related in some way, we have that independent variable impacting our actual dependent variables as well. Our other actual independent variables as well. So imagine like the home example, right? Like the price of a home is dependent on the number of bedrooms, number of bathrooms, square footage of the home, so on and so forth. But now if I increase the number of bedrooms in the home, that will lead to an increase in the number of bathrooms, that will lead to an increase in the square footage of the home as well. So whereas my number of bedrooms, which was supposed to be an independent variable and not affect anything but the price, is now affecting something that I considered as an independent variable. So that is what we call multicollinearity, where essentially one independent variable ends up affecting other independent variables. Okay, All right, so continuing, now I need to identify where these correlations exist in my data, and I need to be able to address those that sort of dependence in my data before I can actually build a linear regression model. And that's just because the whole idea behind linear regression was that an independent variable doesn't affect other independent variables. Let's talk a little bit about how to address that. Okay, so if you just use this correlation function, you are able to see the correlation of different variables with each other and with other variables. So if you look at one column right here, you can see that how the miles per gallon variable is related to different features that we have in our data. Now, these only work with numerical features because you need numbers to actually calculate the relationship or the correlation coefficients. So, okay, let's look at the relationship between, let's say, horsepower and displacement, or let's look at horsepower versus weight. So, it does make sense, right? To increase the horsepower of an engine of the car, you need to add in more things, or, you need to add in more components. And obviously, as your horsepower increases, the weight of the car is going to increase. So essentially what this 0.86 tells me is that for a unit increase in horsepower, the weight increases by 0.86 every single time. So that is an extremely high correlation. And generally speaking, we do not want such type of correlation in our models. And we want to kind of like identify such pairs which have the highest correlation, and we want to address those before we actually build the model. So again, I'm just kind of like showing here what are the pairs that have the highest correlation, just because looking at this entire matrix can become a little challenging. So trying to identify pairs that have higher than 0.75 correlation, I can see that there are a couple of pairs in here that do have that sort of a high correlation. So the ideal thing to do here would be to drop all of these variables from your data to make sure that there is no such correlation in that data, and that your data is actually completely clean. I see that there's a question here. Is model year considered numerical or categorical? That's a great question. Unfortunately, the answer is it depends on how you are trying to use that variable. Generally speaking, when we encounter a variable like model year or anything like that, we try to turn that into another variable called age from current thing. So instead of looking at it as like a year of 1972, we try to look at it as the age of the thing from the current year. And that addresses that problem where we don't exactly know whether it's a categorical or a numerical feature. And I will get to that other question towards the end. So yeah. To group, what if we use parentheses to group independent variables that interact with other independent variables? That is a great point. We have something called interactions, the interaction effect, which tries to account for this, where independent variables are interacting with each other, or have like this sort of a correlation. But that is like advanced regression methods. That's not basic regression. So that's out of the scope of this talk today, but it's called the interaction effect if someone is curious and wants to learn more. Another thing that we can do is we can kind of like plot such a heat map. And obviously, if you look at the color scheme, it tells us that the lightest colors are where we have the highest correlations. Okay, now that we have talked about that, we have to, how do you decide which one to drop? Generally speaking, you want to drop the one that occurs the most frequently in the top pairs. So in here, you can see that kind of displacement is the one that occurs most frequently. So that might be a good one to drop. Is 0.75 the standard? Depends on how rigorous you want to be with this sort of a model. And if you are using this in an intense case where just you can't tolerate any sort of correlations, like in the medical field, where one of these independent effects could cause some unaccounted for things, then you want to be very rigorous. But otherwise, generally speaking, 0.75 would be an ideal thing. So if if two occur 3 times, then you want to look at the correlation with miles per gallon, because miles per gallon was our dependent variable. The one that has the most correlation with miles per gallon is the one that we keep. So in here, you can see that weight has minus 0.83. So essentially, a unit increase in weight reduces miles per gallon. Similar thing with displacement, minus 0.80. I would keep weight and I would drop displacement in that case. Okay, continuing. So I'm just going to pre-process the data. Again, some of these steps are just what we covered. So doing the categorical part, this is called the dummy encoding, essentially. And you can see that after that, I have these things. Now, car name is a thing wherein I have about 100 car names. So what this will do is this will end up creating 100 different columns. I'm not going to do that. Instead, I'm going to ignore the car name entirely. So I'm just going to get rid of these variables and kind of like have this as my final data that is ready to be modeled. Okay, so building out the model is actually fairly straightforward. What I do is I have this sort of a formula where I'm saying that the miles per gallon is dependent on all of these different variables. And that is what I say right here. That is what I put in as a formula. I say that the data comes from this particular data frame right here. And then I go ahead and build the model. This is the R-squared metric that I was talking about previously. So this tells me how good of a model do I have. And then this is the actual model, the statistical model that I have. I will talk a little bit about interpreting this model. But yeah, this is the model that I end up with. This tells me when the model was last run. I have the number of observations that I used to build this model. This DF model is essentially going to be the amount of information that you had, the number of features. And then these are all of the features. Intercept right here is the value when everything is 0. So there's that. And then you have different coefficients right here, which correspond to these betas that we originally saw, beta 1 to beta n. And then for x1 to xn, if you go back to that table, you will see that clearly right here. So these are all of the betas, and these are the corresponding x values. Okay, so interpreting the above model, as I mentioned, the R-squared value, I have a detailed explanation included about the R-squared here, but what I'm going to say right now is the R-squared value just tells you how good of a model were you able to build with your data. Generally, if this value is less than 0.5, that pretty much implies that the model that you have was only able to explain about 50% of the variation in the dependent variable, which is really poor. And anything above generally 0.6 is considered to be a decent model. So you should be able to explain at least 60% of the variation in the dependent variable by using this. And what I mean by that is just the range of values for the dependent variable. If we consider that, if my model can predict fairly well within 60 to 70% of that range, I say that that's a decent model. In here, my model can predict 87% of that values, or my model can explain about 87% of that variation fairly easily. So this is a pretty good model. And again, the amount of data you have does tend to impact how much of an R squared can you get. If you have a low R squared value, it might help to go out and get more data or get more information about the thing. So let's say you are dealing with trying to predict the price of a home, right? You get an R squared of 0.6. You might want to get more information about all of the homes that you have, or the other option would be to get just more information about home sales in general in that area. So yeah. And then the second thing is interpreting the above these coefficients. So notice that the coefficient for weight is negative 0.0052. What this implies is that a unit change in weight is going to end up changing my miles per gallon by about minus 0.0052. Now notice that this is different from the correlation we saw above. This correlation only takes into account weight versus miles per gallon. But when you take into account weight with all of these other things, the impact that weight alone has gets diminished quite a bit. So there is a difference between that. And then, again, origin, you have like different coefficients here. What these imply is that compared to an origin of 1, which we don't see here, if we went with origin 3 car, then your miles per gallon is better by about 2.3 miles per gallon. So you'll get a better mileage by going with a car in origin 3 compared to origin 2 or origin 1, essentially. Again, here, same thing. If you go with a car that is much newer, you get much better mileage compared to some of the older cars. Similarly with cylinders, generally speaking, stays consistent, but for some reason, cylinder 6 seems to have like the lowest mileage out of all of these cars. And then again, displacement, acceleration. As your acceleration increases, your miles per gallon does get better. And as your displacement increases, your miles per gallon does marginally improve. So this was how kind of like, I would look at this model. And some of the other key insights from this model would be, if you want a car that has a great mileage, go for cars manufactured after 1980 and buy a car that has an origin continent of 3. If you want if you're okay with getting a car that doesn't have decent mileage, you can go for a car that was built around 1971 to 1973. And you can go for a car that weighs quite a lot. So those are kind of like the insights that you can gain from this sort of a model. And that is what I mean by the interpretation. There are a few next steps to validating this model. I have included some good sources on the repository that was being shared out. So feel free to kind of like use that. Okay, so there is a question about why origin 1 was dropped. So when we create these columns for category, we end up with something called perfect multicollinearity, where the model can actually guess the category by looking at all. If we give information about all 3, like let's say what happens is what the result will be like. So okay, let's say the actual origin is 1. Then when we make these categories columns, and again, feel free to take a look at this in a little more detail later on. But when we make these category columns, make these show right here. So what that looks like is what that looks like is there are a bunch of zeros and there is going to be one in one particular column, right? Because every single entry can only belong to one category. So if we include every single column, it becomes fairly easy for the model to understand where that relationship is coming from. And that's why we try to exclude one category from each of those categorical variables so that the model is unable to guess which category did that value come from. Is saying that the year has more of an impact than weight. Yeah, that would be a fair conclusion. Yeah, that the year is has a fairly significant impact compared to the weight. No, these are different coefficients. These are not the same as correlation coefficients. The Pearson correlation coefficient is printed out right here at the top when you do data.corr. These are the correlation coefficients. You use years from today. Okay. Yes, it would eliminate, but oftentimes you can construct categories for all of the year variables as well. That is an acceptable technique as well. But yeah, you can create like an age from today as well. That's more relevant if you're going for something like the price of a home, maybe, or something like that. In case of cars, because this data set only contains values from 1971 to 1982, we don't really have that option of looking at it in terms of what the thing would be today. And then you can use Java for these as well, although I'm not sure of what exactly the libraries are. But if you just Google something like Java linear regression, I'm sure you should find something. We use Python much more, but you can do the same thing in RStudio as well, fairly easily. It's just that Python has a lot more applications in the industry as well. So that's why we tend to rely on Python. About solving problems out in the industry using linear regression. Okay, so difference between solving problems in the industry is that you get a lot more data. Here you only have 300 values. In the industry, you would probably have like 1 million values easily. What you see in Kaggle datasets is just a portion of the data. It's mostly just the scale. Also, another thing that's fairly common is in the industry, you don't get data that is fairly clean, and you can't directly jump into the modeling process, but rather you have to spend a significant amount of time trying to clean the data before you can actually use that for modeling. So yeah, any other questions?
In terms of using lots of data out in industry, do you still use Python and Jupyter Notebook, or do you use other tools?
That's a great question. The tools are company specific, although the programming language does stay Python. Jupyter Notebooks are also fairly common. You might end up using Jupyter Notebooks on the cloud, so something like AWS maybe, rather than working on a notebook locally, because that allows you to have a huge amount of computation power rather than just this.
Cool. And do you find you have to take a lot of time to optimize your pandas related code when processing so many millions of data points?
The good thing is that these companies have spent a significant amount of resources trying to come up with tools or with libraries that already have the optimized code. So you won't be kind of like doing that very frequently. When they also have special teams who are kind of like updating that code fairly frequently as well.
Cool. And since running up against
so MATLAB is used fairly commonly as well. Yes,
yeah,
that's correct.
Cool. All right.
All right, so I think that was most of what I wanted to cover.
Cool.
So yeah.
Thank you. Thank you, Abhaneet. Thank you to everyone who joined. Hope you got a lot out of it. If you wanted to connect with folks on LinkedIn, feel free to throw your LinkedIn into the chat as well if you want to connect with folks. But other than that, I think we're all set. Thank you everyone for joining. Have a great night. Feel free to connect with me or email me if you have any questions or anything like that. I'm available on LinkedIn. Abanit is the best way to reach you on LinkedIn.
Sure. Yeah, exact same name as here.
Cool. Yeah. And if anyone wants to connect, ask any further questions, happy to do it. I'll send a follow-up email, and have a great night, or get some sleep if it's 1 a.m., 2 a.m. in your in wherever you are right now. No, 2 a.m. you gotta wind down. You gotta. Also, someone asked about the recording. The recording I will send in 2 business days, so more than likely Monday, just because of back end business stuff. But I will definitely send it to all of you as soon as it's available. It'll be available on YouTube. So thank you, everyone, and have a great night.
Thank you, everyone.